Assalamu alaikum. Welcome to lecture 17 of data mining. So I hope all of you are doing well. So it's getting hot in Lahore these days. It looks like only a month ago it was really cold in Lahore. Now it's really hot. And the hot weather is likely going to continue for the next 7-8 months. So Lahore is hot till maybe the start of October. So anyway, so it's hot today. So today we will be discussing clustering. So we had started talking about cluster analysis last time. Do you have a question, Abdullah?
Yes, sir. Sir, could you explain Minkowski distance? Because in last class I couldn't understand the formula.
All right, sure. We will start. We will start with basic clustering and again go back to the similarity measures again. So okay, so in the last lecture we had started talking about clustering and then we discussed similarity measures or distance functions. So we'll do that again today, and hopefully we will also discuss one clustering algorithm today, the k-means clustering algorithm, which is a very popular clustering algorithm. We will discuss that as well today. So I think that would pretty much cover most of the lecture today, and in the coming lectures we will continue with our discussion on cluster analysis because we will be covering a number of algorithms following in different categories. So okay, so any questions? All right, so let me start my screen. So I'm going to start with the slides to introduce the idea of clustering. These are the book slides, chapter 10 of the book by Han. So what is cluster analysis? So essentially a cluster is a group of objects, or a collection of data objects, and a clustering is a number of groups that you have discovered from the data with the property that within a group objects are similar and between groups objects are dissimilar. So objects are similar or related to one another within the same group or within the same cluster and different or dissimilar or unrelated to objects in other groups. So clustering is generally much more involved than simple segmentation. Oftentimes, segmentation is used as well in data science, but segmentation usually means that you're partitioning your data based on maybe just one attribute value, while clustering is looking at your data with respect to all the attributes and then trying to find the best groupings of objects. So segmentation would be something like you are trying to segment your student population or alums based on gender. So one segment would be male, the other segment would be females. So you can call that clusters as well, but that ideally is not in the technical sense clustering, but that is just based on one attribute gender. But let's say if you're grouping students using multiple attributes, let's say gender, age, GPA, major, their location, their height, their age, and you're trying to find groups based on all of these attributes, then that would be called clustering. So this is the distinction between segmentation and clustering. So segmentation is usually simplistic based on just one attribute, while clustering would typically be based on multiple attributes describing the objects. So this is unsupervised learning if you talk about machine learning. And so it has numerous applications, usually as a standalone tool for understanding data, as well as part of other tasks like in data preprocessing. So for example, in data preprocessing, you can use clustering for, let's say, sampling as well, or data reduction as well. So clustering as its own may be the end goal of your data mining, or it might be a part of your end goal in data mining. So data reduction, so clustering can be used for data reduction. So data clustering, it can also be used for verification of hypothesis. Maybe you have customers' data and you have a hypothesis that this segment or this grouping of people or your customers have this behavior. So you can verify this hypothesis by doing clustering and find out whether those groupings that the clustering algorithm have found actually verify your hypothesis or not. And of course, you can also do predictions based on grouping, although, as I said, this is a secondary goal of clustering. The primary goal of clustering is descriptive in the sense that you want to understand or characterize the data rather than to use it for prediction. So clustering is also commonly used for outlier analysis, and we will discuss outlier after we have finished clustering. So many of the techniques for outlier detection are based on clustering algorithms. So outlier, of course, is any object that is significantly different from the rest of the objects. So that would be an outlier. So uh, you can have various applications of clustering, and these applications can come from all the sciences as well as the social sciences, as well as the business or the humanities. So clustering is one of the most widely applied tasks of data mining. And so here is just a sample of examples. For example, in biology or botany, you can try to group or find groupings of species based on their characteristics automatically. So kind of building a taxonomy of living things just by uh, collecting a data of living things and representing each living thing with a set of properties and sending it to your clustering algorithm. The clustering algorithm would then find groups. Groups are, of course, what? Similar objects or living things, and each group would be dissimilar from the other. So one group might represent a different species or other categorization of animals or things, living things. And in information retrieval, you can think of document clustering. So that is a common application of clustering. So a bunch of documents, you want to group them. And ideally, the group should represent significant topics of discussion in those documents. So one group might be, let's say, computer science, another group might be biology, third group might be chemistry, and so on. And then, of course, you can have applications in GIS, Geographic Information System, trying to find usage patterns, land use patterns, habitation patterns, and so on. In the retail sector, you can think about marketing, trying to find segments of people or your customers who would be interested in particular parts of uh, your product. So again, all of these are applications of clustering. You can even do clustering of, for example, astronomical objects, and based on that clustering, you can maybe find interesting groups of astronomical objects. So again, as I said, it has applications from all domains. So what are the steps required to build a clustering? So when I say clustering, I mean the whole process of dividing data into groups. So that is the whole process. So the first thing is you will need to represent your objects in features. So you have to either do feature selection or feature engineering. So, so this is an important part. So, and this is a general part for any data science project or task. You need to represent objects with their appropriate features. So representation is important. So the next thing that you need to worry about while before starting clustering is the proximity measure or the distance function. Uh, so this is an important component or aspect of clustering. So this is the function that would quantify the similarity or dissimilarity or relatedness between two objects in your data set. And based, of course, on the feature that you have selected. Uh, so if two objects are similar, then this function should give you a high similarity. If two objects are dissimilar, then this function should give you a lower similarity. The third important thing in clustering is the clustering criterion. Remember when we talked about clustering, we said that it was groupings such that one group was cohesive in the sense that it has object that was similar within itself, but it was dissimilar to object in other groups. So how do you quantify this, or how do you uh, kind of make an objective measure out of this? So this is the clustering criterion. So you need to have a criterion, a precise way of quantifying this. You can say uh, intuition of inter-cluster similarity and intra-cluster dissimilarity. So that is the clustering criterion. So most algorithms would have a explicit clustering criterion. And then, of course, you need to have an algorithm that would use your data or that will use your similarity function and the clustering criterion to find the best clusters. So that is a clustering algorithm. And there are a bunch of clustering algorithms out there. We will discuss some of them in this course. And then finally, once you have a clustering, you will need to be able, you should evaluate the quality of the clustering. And you need to validate whether the clusters that are found are really of interest or not. So this is another step, important step. And then, of course, yeah, I mean, that's pretty much it. So then after this, of course, is you need to use the results in whatever application that you want to use your results in. So we'll be discussing all of these steps in this section of our course. So there was a mention of quality in the previous slide. So what exactly is good quality clustering? So what is a high quality clustering? So in simple terms, it should have high inter-class similarity and low intra-class similarity. So intra means that between classes or between groups, and inter means within group. And as I said, we would like to, in most cases, quantify this through a clustering criterion. And that clustering criterion would then be optimized as part of the clustering algorithm. So obviously the quality would depend on a number of things. The similarity measure, this is important from a real world perspective because this is the function that you're using to quantify the similarity between two objects, two real world objects. So maybe the similarity between two students, between two customers, between two websites, whatever your objects are. So if this function is not accurate, then obviously your clustering would not be accurate. And then secondly, of course, the algorithm. So the algorithm should be able to use the clustering criterion and the similarity function to find the best clusters in the data set. So quality at the end of the day, of course, is always evaluated both objectively through the validation process as well as subjectively by the end user, by the data scientist. So both of these things would finally determine the quality of your clusters. So, so what is fundamental in clustering? The similarity or dissimilarity function. Sometimes this is also called the proximity function. And similarity and dissimilarity, of course, are opposite. And so, okay, let me finish this first before going back to, okay. Excellent, just give me a second. Okay, we'll come back to this later. So let's now discuss the similarity functions. So similarity functions are not discussed in chapter 10. They were discussed in chapter 2. So if you look at the chapter 2 slides, so this is the slides here. Towards the end of this slide, you will have a discussion of similarity measures. So this is where I'm going to cover this. I did not discuss this in chapter 2 because at that point, we were not using similarity a lot. So we are now covering it when we are starting clustering. Okay, so let's start first with, of course, similarity measures would be different for different types of attributes. Let's start with numeric attributes. So essentially, before I do that, let me just, so we are representing objects as X. X in general is a vector, which would be bold when you write it in the proper way. So X is a vector. So it would be a vector, let's say X small x. Let me go down here. X is equal to the small, not bold x. Let me say I. All right. Of course, this is a vector x I1, x I2 to x I m. So m is the total number of features representing the ith object, and of course all objects. So in our data set, we will have I is equal to 1 to n. So there will be n data objects, and each object is described by n features. So this is a common way of representing objects as vectors of fixed length m. And of course, I have written this as one object. So if you have collect all the objects together, you will get a matrix, which is called the data matrix. And we have discussed this previously as well. So data matrix is capital X. And of course, in general, whenever we have vectors and matrices, we'll write them in boldface. And so, of course, capital X would be a matrix of n rows and m columns. So in other words, one row of this matrix is the representation for one object. So the ith row is the representation for the ith object. So this is the data matrix. So, and let's assume, as I said before, starting with all attributes are numeric. So for this case, the most general form of, or one of the general form of distance functions, not similarity, dissimilarity, and more appropriate distance function is what is known as the Minkowski distance. So Minkowski distance for, let's say, xi, the ith and the jth object. I'm not writing this in bold or in subscript. I hope you understand. So would be defined as the vector difference xi minus xj. This is a vector difference. Vector usually is a column. So I'm going to take a transpose to make it a row. Okay. So whenever say a vector without any further qualification, we usually assume it to be a column. Okay. Okay. This is not how we define this. This is Minkowski. So, so we have the summation. Okay, summation over all the features k, and so we have x ith k minus x j k raised to power of p bracket, then raised to power of 1 over p. So this is the formula for the Minkowski distance. What is it doing? For each element of the two vectors, it takes a difference and then raises it to some power p. And of course, does this for all the elements. K is equal to 1 to m elements in the vector. And then the sum is then you take the pth root of it. So this in general is called the Minkowski distance. And of course, p is in general greater than equal to 0, greater than 0, not even equal to 0. And usually the common p's that we have, p is equal to 1, 1. So this is called the Manhattan distance. P is equal to 2. This is often called the Euclidean distance. And of course, in functional analysis, this is also called L1 norm, and this is called L2 norm. And in general, when P, we have what is called the LP norm. So the Minkowski distance would always give you a value d, which is greater than equal to 0. Okay? And it would be 0 only when the two objects are the same. Otherwise, it will be greater than 0. So in other words, so d xi would be equal to 0. Otherwise, d would be greater than 0, right? So 0 means that they are similar, exactly same, and greater than 0 means that they are becoming dissimilar, and there is no upper bound actually on this distance or dissimilarity. The other property of this measure is what is known as the symmetry property. Xi, xj, this is equal to d xj xi. So this is called the symmetry property. Okay. So it doesn't matter if you have one value at the starting, one object at the starting object as opposed to the other object. You will get the same distance between them. And the third property is what is known as the triangle inequality. So d xi xj would always be less than equal to the sum of d xi xk, some other k which is not equal to I and j, plus d xk to xj. So you can think of k as some other point. And then if you go from x1 to xk, that other point, and then to xi to xk, and then from xk to xj, the sum of those two distances would in general be greater than or maybe equal to the distance, the direct distance between xi and xj. So this is called the triangle inequality. Triangle. So we have the symmetry property, the triangle inequality, and then of course the first property where distance should always be greater than or equal to 0, and it's equal to 0 when, if and only if the two objects are the same. So together these three properties are desirable in a distance function or a similarity function or a dissimilarity function. And when these properties hold, we call the function a metric. METRIC, metric. So it's a metric function. So you might see this terminology used in the literature. So why are these three properties desirable? Obviously, they're very intuitive. So if two objects are same, their distance should be 0. Otherwise, their distance should be greater than 0. Of course, since we are talking about distance, distance is not a asymmetric property. It is a symmetric property. So x1, x2, if they are flipped, the distance should be the same. Similarly, if we are trying to find the distance between 2 points, if you go through some other path, that distance would be generally greater. So that is a triangle inequality. So these three properties are desired in a good distance function. And they are desired and recommended, but in many or in most clustering algorithms, it's not an absolute necessity. You might have some functions that are not truly metric, but still your algorithm would work. Okay. So any questions? So if you have attributes that are all numeric, then this is the common measure. Of course, there's another measure which is called the Mahalanobis distance. So Mahalanobis distance is actually the distance, the Euclidean distance, the Euclidean distance between objects when objects in the data set are normalized so actually we talked about normalization previously. So there are various ways of normalization. So z-score normalization plus decorrelation. So if you do this and then compute the Euclidean distance, then this is called the Mahalanobis distance. And in terms of so Mahalanobis distance of xi, xj, it's simply xqrt xi minus x. Now this is in vector form. Xj transpose the covariance matrix, the inverse of the covariance matrix, is used to normalize the two vectors. So xi minus xj. So this is the formula for the Mahalanobis distance. So in other words, you have a normalizing factor, which is a covariance matrix. And of course, if you don't normalize, then it is the Euclidean distance. So Mahalanobis distance is actually more common for computer vision. It's less common in general data mining because of the decorrelation impact. Because usually decorrelation tends to obfuscate your patterns in the data. Of course, for computer vision, it has some other benefits, but for most other data mining, decorrelation is not desired. So, but anyway, so you need to know that there is a Mahalanobis distance measure as well. If your data set consists of images and videos and other related stuff, you might want to consider using this. Okay, so now let's talk about our nominal attributes. So again, we are assuming that all attributes are nominal, meaning that you have x1. Now again, so again, let's say m is equal to 2. So we have x I1 and x I2. Okay? And let's say x1, this is, I'm talking about the feature, not the object. X1, let's say, is a, it's, let's say, color, which is a nominal attribute. And let's say x2 is, let's say, again, taking some simple example, is GPA, for example, not GPA, grade. Of course, grade is nominal as well as ordinal, but here let's consider it to be nominal. Let's take something else as what else? Okay, that's fine. Okay, so if you have all nominal attributes, you can simply do simple matching. All right, so what we have is what is known as a simple matching coefficient. So in that case, basically the similarity now between xi and xj, not dissimilarity, similarity, is basically defined as a number of attributes with exact matches divided by m, of course, the total number of attributes. So let's say हमारे पास दो ऑब्जेक्ट्स हैं, एक ऑब्जेक्ट कलर लेट्स से रेड था और दूसरा जी ग्रेड उसका बी था, and let's say we still have a red and a grade is C. So what would be the similarity here? Similarity would be 1 over 2. So red is one match and of course, grade is not matching. Total number of features is 2. So this is similarity. It is obviously normalized. So if you want to convert it to dissimilarity, so dissimilarity would simply be 1 minus similarity. Okay. So this is for the case when you have nominal attributes. So let's say if you have binary attributes. So binary is a special case of nominal. In this case, of course, you can still use simple matching coefficient. Okay. But you can also use the many other measures that we studied as part of association mining. Do you remember those measures? So we talked about, for example, Jacob coefficient. We talked about the Sorensen dice. We can also compute the cosine and so on. So all of these measures can also be used to quantify similarity when you have binary attributes. So in other words, you create the contingency table, matches, no matches. And from there, you can compute any of these measures. So contingency table, for example, so for example, so how should I write this? Let me see. So you will have on the rows, so for example, matches. No, just a second. So you will have different objects, for example. So distance. So let's say we have on the row is xi, right? The row is xi. So if xi has any value, may have multiple values, right? But if that value matches with the other, let's say it has value, let's say A, B, and C, and so attribute A, B, and C, let's say, or actually you can do this in different way. So basically you have matches here and you have non-matches. And then of course the column would also be for the other attribute you have matches and then you have not matches. And then you write the count. How many attributes of xi and xj match? So that will be there. How many attribute of xi is different from that? You write it there. And then from this table, you basically can compute all the measures. So you can have A, B, C, and D. And of course, all of these A, B, C, D would sum to the total number of attributes M. Okay? M is the total of attributes in your data set. So for binary attributes, you can do that. Of course, there is a slight distinction that is sometimes used. If you have asymmetric binary attributes, then you do not count the matches of one value. So for example, the value 1 is considered more important than value 0. Then if 0, 0 matches, you do not count it as a match. Only you count the match of 1, 1. So this would be the case if you want to emphasize a matches of 1, 1 and not the matches of 0, 0. And typical example that is given for this is for, let's say, medical testing. So for example, medical diagnosis, you have, let's say, test A, test B, and let's say test C. And let's say you have two examples. This is 1, this is 0, and this is 0. And this is 0, this is 0, and this is 0. Second object. First object has 1, 0, 0. So object test A is positive for person 1, while B and C are negative or 0. And second person has all the tests as negative. So in this case, if we want to compute the similarity, we do not count the similarity of 0 and 0. So similarity in this case would be so actually in this case we will be computing dissimilarity actually. So dissimilarity here would be the one that you saw that's a different 1 and 0 over 3. So you will not count the similarity of, and dissimilarity of course would be 2 over 3. Sorry, similarity would be 2 over 3. Actually this was, just a second, making a mistake here. Yeah, so we are finding a similarity between the two, so you won't be counting those two as similar. So similarity of course here would be 0, 0 over 3. So you do not count the similarity of zeros and zeros. Only if 1 and 1 were same, you count it as similarity. So if I change this, let's say D attribute भी है और इसमें यहाँ 1 है और इसका भी 1 है. Now the similarity would be 1 over 4. So you do not count the similarity of matches of zeros as zeros. So this would be asymmetric, and this, as I said, would be appropriate if your matches of a particular value is more important or significantly more important than the matches of the other value. So this is asymmetric. So what about if you have ordinal attributes? So ordinal attributes, a typical example is like, let's say the grade. Okay, so grade typically would be ordinal between A, B, C, D, and let's say F. So, and there is a specific rank in these values. So for ordinal attributes, so we basically convert it into numbers and then apply a simple difference. So how do you do that? Let's say we have two objects. Let's say person A, P1 का grade B था और P2 का grade, let's say, D था. ठीक है? So how would I compute the dissimilarity between them? The dissimilarity between P1 and P2 would simply be, so I will convert these values to numbers. So I would, since there are 5 possible values, so I would give A the value of 1, B 2, 3, C, D would be 4, and F would be 5. So in this case, so B and D, okay? So this would simply be the absolute difference between the values, which is 4 and 2, okay, divided by, so we have 5 possible values. So divided by the maximum that you would have would be 5 minus 1, 4. So we'll have 2 over 4, which will be 1 over 2. Okay, so this is the dissimilarity between the two objects if the objects are represented by ordinal attributes. So in other words, you're converting them to numbers and then just taking the difference of those numbers. Of course, normalizing with the total number with the maximum possible difference. The maximum possible difference is what? 5 minus 1, 4, which is in the denominator. Okay. So this is ordinal. And then finally, and of course, these measures are some of the common measures. You might have some other measures that are used in practice. Uh, you can always study them. So we are already discussing the commonly used measures. So what happens if you have mixed attribute types? So previously we have discussed that all attributes were numeric or nominal or binary or ordinal. So what happens if your objects are described by attributes of different types? So maybe some are numeric. For example, you have age, let's say, and let's say you have gender, which is binary, and then let's say you have something else, let's say grade, which is ordinal. So for mixed attribute types, again, there might be multiple measures. One simple way is to combine them using a weighted average approach. To take the difference, dissimilarity between attribute wise, and then take the weighted average. So for example, if it was numeric, let's say if we talk about age, so let's say one age was 50, the other age was 30, we will simply have 50 minus 30 divided by, of course, the maximum difference that is possible in the data. So max difference so let's say the max difference, of course, was, let's say, ऊपर 20 आ गया, नीचे let's say max difference was 70. So this would be your dissimilarity for this particular attribute only. Similarly, for ordinal, we have already discussed approach. For binary, you already have an approach. So then once you have done that, you simply now, and you have to make sure that each attributes का जो भी dissimilarity आ रहा है, it is properly normalized. और similarity use करें तो properly normalized है, dissimilarity normalized है, ठीक है? So if it is properly normalized between 0 and 1, then you can simply combine the scores for each attribute. So let's say we have dissimilarity for dissimilarity for, let's say, attribute. So D for, let's say, age. So plus D for आपका gender plus D for क्या था तीसरा grade. And then of course weighted average ले सकते हैं इसका, weighted भी ले सकते हैं, then you can also do a simple average which is 1/3. Okay. So if you have mixed attributes, you can define your dissimilarity in this way. Compute similarity for each attribute separately. Make sure it is normalized. This is very important because otherwise एक attribute दूसरे attributes के साथ compare नहीं कर पाएगा. One value might be very large, the other value might be very small. So make sure they are normalized. Then you simply take the weighted average or simple arithmetic mean if you don't have any different weights for different attributes. So that was, I think, all for the similarities. Of course, for some other domains, if your objects are described as documents, and if your objects are some more complex types like graphs, then you will have to have its appropriate similarity function. And once you have that similarity function, you can go ahead and apply clustering algorithms. So you can put all the similarity or dissimilarity values in a matrix. So if you do that, you have what is known as a dissimilarity matrix. So let's say I call this matrix D. And of course, in general, matrix would be capitalized. Okay. So, so the Dij, which is one element in this matrix, is basically the dissimilarity between xi and xj. Okay. And if your function D is metric, then this matrix, of course, would be symmetric, because as you know, dxj and xi would be the same. Okay. So this matrix would be of size what? This is M, kitne features? Sorry, M neither. N objects by N matrix. So for many clustering algorithms, even if you're given the dissimilarity of matrix, you can apply your clustering algorithms. You don't need the feature representation for each object. Okay. For many, not all, आप directly apply work कर सकते हैं on the dissimilarity matrix. So one of the good things about this is that maybe the matrix D may be specified by humans. So maybe you don't ask, you have not computed these values through some algorithm or so through some function. You ask humans to give them values. So let's say कोई आपके पास complex data set है, but and that for which you can't quantify the similarity between two objects. You just ask humans to fill this matrix, assuming, of course, this matrix of reasonable size. If it is massive, of course, you can't fill it out. And once you have this matrix filled out, you can do clustering on the data. Okay? So in other words, you don't need to have a distance function or a dissimilarity function explicitly if you want to do clustering, as long as you have those distance values or dissimilarity values for the objects in your data set. Okay. All right. Any questions? All right. So now coming back to clustering. So, so we have talked about the similarity function. Now let's talk about so actually in clustering, you can do categorizations or classifications in different ways of the techniques, of the methods, and so on. So, so let me start with uh, types of clusterings, types of clusters, let's say. So clusters can be defined in different ways. Of course, intuitively, what is a cluster? A cluster is a group of objects that are similar to each other. Okay? So from an algorithmic perspective, we'll need to properly or precisely define a cluster. So there are 2, 3, 4 ways of, you can say, defining clusters. One of them is called prototype clusters. So in prototype-based clusters, a cluster is represented by a single or at most a few representative objects within it. Okay? So actual objects objects slash points. So objects are actual objects and points may not be actual objects, but there are some points in that space in which those objects lie. Okay. So let's see. So basically, let's say if you have a cluster like this, which have multiple points in it, so you can represent it with some representative object or a point. It might be the central point in this group, so which I've drawn as a plus. So it could be the mean. What is the central tendency of data? It could be the mean, it could be the median, it could be the mode. Okay. So if you want to represent it with more than one points, so maybe then you can represent it with a central point and maybe some boundary points, so that it captures, let's say, the shape of the cluster more appropriately. So such types of clusters are called prototype-based clusters. They are represented, they are modeled with one or maximum a few points. If it is one, then it's a centrally located point. It might be the mean, mode, median. And if it is more than one, then usually some point that capture the contour of the cluster. Another way of characterizing clusters is through density-based clusters. So as the name suggests, a cluster is a dense region of objects. So whenever you talk about density, then it's based on number of objects as well as the space in which those number of objects lie. The density is quantified by two things. So let's say if you have a large number of points, but they also lie in a huge amount of space, then it may not be dense. So large amounts of points must lie in a smaller space, then it will be dense. So we can represent clusters through density as well. If the density is greater than some threshold, then that means that that region is a cluster. So this is another way of representing clusters. And finally, of course, there may be other as well. So graph-based clusters. So here again, as the name suggests, we use notions of graph connectivity to determine clusters. So cluster is a you can say strongly connected region of objects. So so graph-based consider all objects as well as their similarity between the objects. So you think of two objects and a line between them. That line captures the strength of similarity between those two objects. And then together, if that strength is very high, then that would be a graph, that would be a cluster, otherwise it will not be. So both connectivity and the strength of the connectivity is important. So actually, if you look at this sequence, so prototype based is the simplest way of representing clusters or uh, defining clusters. Then we have density based, which are more sophisticated, very more comprehensive, and then graph based, which are more comprehensive. And then, of course, some algorithms, as we'll discuss, would focus primarily on prototype based clusters, others would focus primarily on density based clusters, and others would focus on graph based clusters. Uh, very briefly, types of clusterings. So we said types of clusters. So we had talked about three types. The types of clusterings, generally we have what is known as hard versus soft clustering. So hard clustering means that you partition the data set such that each point should lie in exactly one cluster. So in other words, so let's say if you have 3 points, let me represent those points with numbers 1, 2, 3, and 4. Let's say 4 points. And let's say if I want to partition them into two groups, then group 1, let's say, has 1 and 3, and group 2 has 2 and 4. So object 2 lies in group 2. Okay? It does not lie in group 1. So this is hard clustering. Every object will lie in just one cluster. And most algorithms do hard clustering. Of course, some of them can be modified to do soft clustering. So what is soft clustering? Soft clustering would mean that group 1 में आप कहेंगे object 1 है and assign a probability. Let's say probability for this is 0.8 and 3 है, इसकी probability है 0.9. ठीक है? And let's say also 2 भी है इसके अंदर, उसकी probability है let's say 0.2. And similarly group 2, इसमें 2 है, इसकी probability 0.8 है, इसके अंदर 1 भी है, इसकी probability 0.2 है, और what else, 4 है, let's say इसकी सारी probability 1 सारी इधर ही है. So now you notice that an object may be placed in multiple clusters, but then you will need to assign a confidence value to that object, how confident or how likely that object lies in that cluster. So this is soft clustering. An object can lie in multiple clusters. Okay. And then again, types of clusterings. So this is types of clustering. So types of clustering algorithms, algos, I should say categories. Again, there might be different ways of categorizing the algorithms. So we will follow, we will use one technique, which is partitioning partitioning algos. So this is one category of algorithms that work by partitioning the data set. And then we have another category which is called hierarchical clustering. इसको clustering ही कह देता हूँ, because they also have specific characteristics about the clusters that they form. So these are the two main categories of clustering algorithms: partitioning clustering algorithms and hierarchical clustering algorithms. There might be others as well, for example, density clustering, and for example, graph clustering and model clustering, and so on. But the most common and the two main categories are partitioning clustering and then hierarchical clustering. So we will discuss their characteristics as we move forward. So we are about 10 minutes into the lecture, end of the lecture. Any questions so far? So partitioning algorithms are, as I said, partition the data set. So what is our data set? Let's say data set is essentially your X. I is equal to 1 to n. Okay? So n data objects. So the partitioning algorithms would partition this data into some fixed number of clusters or groups. And we usually have to assign or fix the number of clusters a priori. So k clusters, let's say. So usually k has to be specified a priori. Okay? Meaning that as before you apply the algorithm, you need to provide k as a parameter to the algorithm, and the algorithm would then output k groups from the data, k clusters from the data. Okay. So such algorithms are called partitioning algorithms, and we will discuss a few of them. Most of or many of them are prototype based in the sense that they work on clusters that are represented by prototypes. In the more general sense, so let's say you have n objects and you want to form k clusters. So how many possible combinations can you have? So this is a combinatorics question. Uh, so so I think you probably have to have n choose k clusterings that are possible. So n choose k would typically be a large number because n, of course, is very large. So n, let's say, is let's say 10,000, 1, 2, 3. And let's say k is usually, let's say, around 10 clusters. So 10,000 choose 10, 10,000 factorial divided by 9,990 factorial and divided by 10 factorial would be a massive number. So these are the possible number of clusterings that you can have. But of course, all of those clusterings are not of interest to us. We would like to find those clusterings which satisfy our criterion. And our criterion in layman terms was objects within a cluster are similar, objects between clusters are dissimilar. So in most partitioning algorithms, we will define this criterion explicitly as an objective function and then solve this problem, uh, which is optimization problem in an iterative fashion. Okay. So I think I'll stop here. In the next class, we will start with discussing with the k-means algorithm, which is a representative, which is a popular clustering algorithm, which is a partitioning clustering algorithm, which is prototype based, and it is commonly used in many applications. So we will discuss this in the next lecture. And so I think that's pretty much it. Any questions? Any questions? So this is chapter 10 of the handbook. Plus clustering, I would strongly recommend, and one part actually is mandatory, but I would strongly recommend that you also read this chapter from the other book, Introduction to Data Mining, because that is written in somewhat better way, in more, I would say, in a more logical way. So इंट्रोडक्शन टू डेटा माइनिंग में जो क्लस्टरिंग का चैप्टर है वो आपने जरूर पढ़ना है, ठीक है, इन एडिशन टू द चैप्टर 10 फ्रॉम हैंडबुक. Any questions?